There is something wrong with the air over the western Atlantic tonight. Not in the way a typical storm feels wrong. Not the kind of low pressure that spins up and brushes past the outer banks before tilting northeast into the fishable void. This is different in a way that forecast models do not like. A way that makes the word bomb cyclone feel almost nostalgic, almost comforting. Because a bomb cyclone is at least a known quantity. A bomb cyclone is a mechanical event, rapid intensification, pressure falling 24 millibars in 24 hours, a tightening circulation, a conveyor belt of moisture wrapping into cold air. It is violent, but it is familiar. What is headed for the East Coast over the next 72 hours carries a different signature entirely. One that the technical literature has names for, but that operational meteorologists rarely say out loud without a pause. The pause is what matters. The pause is where professional judgment meets something that the physics says is possible, but that experience says should not be happening on the last weekend of May. Snow flurries in the forecast for western Massachusetts and the Berkshires, for the higher terrain of Vermont and New Hampshire, for the spine of the Appalachians down into West Virginia. Snow flurries on the final weekend of May. That sentence alone should stop you, not because snow in May is impossible. It has happened before. A late-season cold snap, a trough digging deeper than expected, a few inches in the mountains that melts by noon. That is not what the models are showing. What the models are showing is a thermal collapse so abrupt, so vertically coherent, that the atmosphere will behave as if the calendar has been thrown backward into early March. The difference between a typical late-season cold snap and this event is the difference between a door left open and a wall being removed. One lets cold air leak in. The other fundamentally reconfigures the thermal structure of the lower atmosphere over a 1,000-mile swath. Let me give you the numbers that explain why forecasters are losing sleep. 3 numbers, not 20 parameters, not a spaghetti plot of ensemble members, not a probabilistic matrix. 3 specific numbers that, taken together, describe an atmospheric configuration that has no business existing in the last week of May. Number 1. The pressure rise behind the cold front. Not the pressure fall ahead of the storm, which is what bomb cyclones are famous for. The pressure rise. The post-frontal pressure surge. Models are showing 5 to 7 millibars of pressure rise in 3 hours as the cold air slams into the coastal plain. 5 to 7 millibars in 3 hours is not a front. It is a wall. It is the atmospheric equivalent of a freight train hitting a concrete barrier at speed. Number 2. The low-level lapse rate. 8 to 10 degrees Celsius per kilometer from the surface, up to about 700 meters. If those numbers do not mean anything to you yet, let me translate them. A lapse rate that's steep in the lowest kilometer of the atmosphere means that the air is thermodynamically inverted from its stable state. It means that the atmosphere does not want to stay stratified. It wants to mix violently. It wants to overturn. The technical term for that configuration is potential instability, but the plain language translation is that the air mass will produce wind gusts that have no relationship to the gradient wind predicted by the pressure field. The ground will experience winds that the upper-level flow does not predict. That is a dangerous condition. That is a condition that brings trees down across roads, that turns Memorial Day camping trips into survival situations, that takes the roof off a barn in a place where barns have stood for 100 years. Number 3 is the one that makes experienced meteorologists uncomfortable in a way they cannot fully articulate: the altitude of the low-level jet. In a typical spring storm, the strongest winds are found somewhere around 850 millibars, roughly 1,500 meters above the surface. In this event, the models are collapsing that jet downward to 925 millibars, sometimes 950 millibars. That is between 6 and 800 meters above the ground. That is well within the reach of terrain. That is an altitude where the wind field interacts directly with the physical geography of the eastern seaboard, where the flow separates around the White Mountains and accelerates down the leeward slopes, where the gap winds through the Mohawk Valley, turned from a forecast problem into a structural engineering problem. A low-level jet at 925 millibars in May is not a statistical outlier. It is an event that should not appear in the climatology. It belongs to November. It belongs to March. It belongs to the cold season when the thermal gradient between the continent and the Gulf Stream is at its maximum. It does not belong to the last weekend of May, and yet the models have been consistent for 4 consecutive runs that something very close to this configuration is going to develop. Now pause here for a moment and consider what consistency across 4 model runs actually means in operational meteorology. The Global Forecast System, the European Model, the Canadian Ensemble, the High-Resolution Rapid Refresh. 4 different physics cores, 4 different initialization schemes, 4 different ways of parameterizing the subgrid scale processes that cannot be explicitly resolved. When all 4 converge on the same anomalous structure, the statistical probability that the structure is a model artifact collapses. The models are seeing something real. The question is not whether the structure will develop. The question is what that structure will do when it encounters the thermal memory stored in the soils of the Northeast Corridor. And this is where the story takes a turn from local weather into something broader. Something that connects this single weekend event to a pattern that has been quietly assembling itself for the past 18 months. If you live anywhere within a few hours of the I-95 corridor from Washington to Boston, this weekend is directly relevant to your plans. You should be watching the forecast updates closely. But if you are watching from anywhere else in the country, from the plains or the Southwest or the Pacific Northwest, you need to keep watching too. Because what is happening here is the eastern face of a hemispheric circulation pattern that is holding the entire mid-latitude weather machine hostage. The same configuration that is going to produce snow in the Berkshires in May is the same configuration that has been delivering atmospheric rivers to California in February, and heat domes to the Pacific Northwest in June, and cold air outbreaks to Texas in February. It is not 4 different problems. It is one problem expressing itself through 4 different hazard types at 4 different times of year. The atmosphere does not care about the calendar. The atmosphere does not know that this is Memorial Day weekend. The atmosphere is running its physics, and the physics are telling us that the large-scale wave pattern has become locked into an amplitude that the jet stream is not supposed to maintain outside of winter. Let me explain what that means in terms that do not require a degree in atmospheric dynamics. The jet stream is not a single continuous river of air. It is a wave. It meanders north and south as it circles the hemisphere. In summer, those meanders are small. The wave amplitude is low. The jet sits at higher latitudes, and the mid-latitudes experience relatively stable, warm conditions. In winter, the wave amplitude increases. The jet plunges southward over the continents and arcs northward over the oceans, bringing cold air down from the Arctic and warm air up from the tropics. That is normal. That is seasonal. What is not normal is to have winter-level wave amplitudes in late May. What is not normal is to have a ridge building over the Canadian Maritimes so strong that it blocks the eastward progression of troughs, forcing them to stall and dig and amplify beyond anything the calendar would predict. That is what is happening right now. A blocking high over the North Atlantic, positioned exactly where it should not be for this time of year, is acting like a boulder in a stream. The flow cannot go through it. The flow must go around it. And when the flow goes around a stationary block, it has no choice but to amplify the wave downstream. The downstream expression of that amplification is a trough digging all the way down into the southeastern United States, a trough so deep that its base extends into the Gulf of Mexico, a trough that will be so vertically stacked and so thermally coherent that it will pull air down from the stratosphere into the mid-latitude troposphere. That last sentence is important. Stratospheric air. Air that has never touched the planetary boundary layer. Air that has been sitting above 50,000 feet for months, cold and dry and chemically distinct. When that air descends into a deepening trough, it does not mix gradually. It descends as a coherent filament, sometimes less than 100 miles wide but thousands of miles long, and it brings with it the thermal properties of the lower stratosphere. Temperatures at 5,000 feet that should be above freezing in late May will instead be below -10 Celsius. Temperatures at the surface will not just drop, they will collapse. The models are currently projecting that the temperature at 2 meters above ground in parts of western New York and northern Pennsylvania will fall from around 65 degrees Fahrenheit on Saturday afternoon to below freezing by Sunday morning. A 30-degree drop in less than 12 hours. That rate of change is not uncomfortable. It is physiologically dangerous for anyone caught outside without adequate clothing. It is agriculturally destructive for the early season crops that have already been planted. It is infrastructure threatening for the transportation networks that have already switched over to summer maintenance schedules. The salt trucks are not ready. The road crews are not staffed. The assumptions that govern late May operations are based on a climate that no longer exists, or at least not a climate that behaves the way the calendar says it should. And yet, even as I say that, I want to be careful not to overstate. This is not a climate change screed. This is not an argument about attribution or long-term trends. This is an observation about a specific atmospheric configuration that is happening right now. And the question I want to hold in front of you is not what this weekend looks like. The question is what this configuration implies about the rest of June. The question is whether the large-scale wave pattern that is producing this anomalous late May trough is going to persist, whether the blocking high over the North Atlantic has established itself as a semi-permanent feature for the early summer, whether the jet stream has entered a regime that we do not fully understand and that the seasonal forecast models did not anticipate. Those are the questions that keep operational forecasters up at night. Not the storm itself. The storm is a known quantity. The physics of extratropical cyclones are well understood. The questions are about the boundary conditions, about the large-scale flow that sets the stage, about whether the atmosphere has shifted into a configuration that lies outside the envelope of typical seasonal variability. Let me take you inside the forecast office for a moment. Not because the internal dynamics of NOAA are inherently interesting, but because the language that forecasters use when they are worried is revealing in ways that raw data cannot be. The public products are measured. They will mention unseasonably cold temperatures, gusty winds, the possibility of snow in the higher elevations. They will not mention the technical discussions that happen on the internal coordination calls. On those calls, forecasters use words like anomalous and unprecedented, and outside the climatological distribution. They talk about the 850 millibar temperature anomaly, which in this event is projected to reach -3 standard deviations below the 1991 to 2020 mean for the last week of May. 3 standard deviations. That is not a cold snap. That is an event that the statistical distribution says should happen less than once every 300 years. And yet here it is, happening in front of us, happening in a year that has already produced a February cold outbreak in Texas that exceeded -4 standard deviations, and an October heat wave in the Pacific Northwest that exceeded +4 standard deviations. The tail of the distribution is not what it used to be. The extreme events are no longer extreme. They are becoming the new boundaries of the possible. But I want to be precise here, because precision is the only defense against the kind of vague alarmism that makes viewers tune out. The statement that an event is a 3 sigma anomaly does not mean that the climate has collapsed or that the planet has entered an irreversible spiral. It means that the statistical model we built based on the past 30 years of observations is no longer a reliable predictor of the present. The envelope of variability has changed. The question is whether that change is temporary or permanent, whether it represents a shift in the underlying distribution or simply a particularly wild excursion that will snap back to something resembling normal by July. The honest answer is that no one knows. The honest answer is that the models cannot agree on whether the North Atlantic block will break down in 10 days or persist for 6 weeks. The honest answer is that we are watching a real-time experiment in atmospheric dynamics, and we do not know the outcome. That uncertainty is not a failure of science. It is a feature of complex systems. The atmosphere is a chaotic fluid. Small errors in initial conditions grow exponentially. The butterfly effect is not a metaphor. It is a mathematical property of the Navier-Stokes equations that describe fluid motion. The practical implication is that there is a fundamental limit to how far into the future we can predict the detailed behavior of the atmosphere. That limit is not a technological problem that better computers will solve. It is a mathematical limit imposed by the structure of the equations themselves. We cannot know with certainty what the weather will be 3 weeks from now. We can only know the statistical distribution of possible outcomes, and that distribution is only as good as the model that generates it. If the real climate has shifted into a regime that the model was not trained on, if the model's physics parameterizations were calibrated on a past climate that no longer exists, then the distribution is wrong. The confidence intervals are meaningless. The forecast is a guess dressed in the clothing of mathematics. This is the deeper implication that no one wants to talk about on the evening news. It is not that the storm is coming. The storm is coming. It is not that the snow in May is unprecedented. It is statistically anomalous, but not unprecedented. The deeper implication is that our ability to anticipate the future behavior of the atmosphere is decaying in real time because the assumptions that underpin our predictive models are becoming invalid. The models assume that the climate is stationary, that the statistics of the past are the statistics of the future. That assumption was never strictly true, but it was close enough for operational purposes for decades. Now the departure from stationarity is happening faster than the models can adapt. The reanalysis data that we use to train our parameterizations lags by several years. We are building models to predict a climate that no longer exists, and we are discovering that the climate of the present is not well represented by the climate of 2018 or 2019, or even 2021. Let me give you a concrete example of what this looks like in practice. The parameterization of convective available potential energy in the global forecast models assumes a certain relationship between surface temperature and mid-level lapse rates. That relationship was derived from observations taken between 1980 and 2010. It worked well for decades. In the past 3 years, the observed relationship has shifted. The same surface temperature now produces higher instability than the models predict because the mid-level lapse rates have steepened. The atmosphere has become more conditionally unstable for a given surface temperature. The models do not know this. They are still using the old relationship. So when the models forecast thunderstorm potential, they systematically underpredict. They miss the most intense storms because the physics core was calibrated on a world that no longer exists. The same problem appears in the low-level jet parameterizations, in the boundary layer mixing schemes, in the radiation codes that account for cloud feedbacks. Every component of the forecast system was built on assumptions of stationarity, and stationarity is failing. This weekend's storm is a symptom of that failure, not the cause, not even the most dramatic symptom, just the most recent one. The snow in May is a signal. It is telling us that the thermal structure of the atmosphere has shifted, that the cold air reservoirs at high latitudes are not behaving the way they did 20 years ago, that the jet stream is amplifying more readily and staying amplified longer. The signal is real. The question is how we interpret it. One interpretation is that this is just weather, just the natural variability of a chaotic system, just a rare alignment of factors that will not repeat for another century. Another interpretation is that the underlying statistics have changed, that the envelope of possible weather has expanded, that the rare events are becoming less rare. The data support both interpretations. The data do not yet tell us which one is correct. That is the uncomfortable space where we live now. Between the signal and the noise. Between the event that is happening and the pattern that may be emerging. I want to take you deeper into the mechanics of this specific storm, not because the mechanics are the point, but because the mechanics are the gateway to the larger questions. The bomb cyclone that will develop off the coast of North Carolina over the next 24 hours is going to intensify at a rate that meets the official definition of explosive cyclogenesis. 24 millibars in 24 hours. That number is important because it separates ordinary storms from the kind that produce damaging winds and coastal flooding. But the intensification rate is not the most interesting thing about this cyclone. The most interesting thing is where the intensification is happening relative to the upper-level support. In a typical bomb cyclone, the surface low deepens beneath a pre-existing upper-level trough. The trough provides the dynamical forcing. The surface low responds. In this case, the relationship is inverted. The surface low is going to deepen first, driven by the thermal contrast between the warm Gulf Stream waters and the cold continental air pouring eastward across the coastal plain. The surface deepening will then induce a response in the upper levels, stretching the column, creating a vortex that propagates upward rather than downward. This is called a bottom-up cyclone. It is less common than the top-down variety. It is also more difficult to predict because the physics of upward influence are less well understood than the physics of downward influence. The practical consequence of this bottom-up development is that the storm will be vertically stacked earlier in its life cycle. A vertically stacked cyclone has the low-pressure center aligned directly beneath the upper-level vortex. There is no tilt. In a tilted system, the dynamics are spread out. In a stacked system, the dynamics are concentrated. Concentrated dynamics produce tighter pressure gradients. Tighter pressure gradients produce stronger winds. The models are currently showing that the storm will achieve vertical stacking by Saturday evening, just as the low reaches its maximum intensity off the coast of Long Island. That timing means that the strongest winds will coincide with the period of maximum thermal contrast between the storm's warm sector and the cold air wrapping around its western flank. The result will be a wind field that does not decay with distance from the center in the normal way. The winds will extend further west, further inland, than the pressure field alone would suggest. The trees in western Connecticut and the Hudson Valley will experience gusts that the gradient wind equation does not predict. That is the lapse rate effect I mentioned earlier. The steep low-level lapse rates will allow momentum from the upper levels to mix down to the surface, bypassing the usual frictional constraints. Now let me translate that into something you can feel. On Saturday night, if you are in the corridor from Albany to Scranton to Binghamton, you will experience wind speeds that do not make sense given the pressure reports on your phone. The barometer will be falling, but not dramatically. The pressure gradient will be significant, but not historic. And yet, the wind will howl. The wind will roar. The wind will knock down trees that have survived every storm of the past 30 years. That is not hyperbole. That is the physics of a well-mixed boundary layer beneath a steep lapse rate. The momentum from the low-level jet at 925 millibars, the jet that should be at 1,500 meters, but is instead at 800 meters, that momentum will reach the surface almost undiminished. The trees in your front yard do not care about the pressure gradient. They care about the wind speed at their tops. And that wind speed will be 40, maybe 50, maybe 60 miles per hour in places that have no business seeing those numbers in May. The snow that falls in the higher elevations will be a different kind of problem. Not because the accumulations will be crippling. The models are calling for 4 to 8 inches in the highest terrain of the Adirondacks and the Greens, less in the Berkshires and the Poconos. Those numbers are not paralyzing. They are manageable. The problem is the character of the snow. With temperatures at the surface hovering near freezing and temperatures at 5,000 feet below -10, the snow will be the wet, heavy variety. It will stick to everything. It will accumulate on trees that have already leafed out. A fully leafed deciduous tree in late May has a surface area for catching snow that is orders of magnitude larger than the same tree in December. The weight of 4 inches of wet snow on a canopy of fully expanded leaves is not a trivial load. It is a load that breaks branches. It is a load that brings down power lines. It is a load that transforms a modest snowfall into a major infrastructure event, because the trees were not designed for this. They evolved to handle snow in winter, when their branches are bare. They did not evolve to handle snow in May. Their structural integrity assumes a different seasonal loading. That assumption is about to be violated across tens of thousands of square miles. The power outages will be the story that lingers after the wind dies and the snow melts. Not the wind itself, not the snow itself, but the duration of the recovery. Utility crews in the Northeast are staffed for late May, as if late May is a low-risk period. They are not prepared for widespread wind damage combined with heavy wet snow on leafed-out trees. The restoration times will be measured in days, not hours. And here is where the narrative opens into something larger, something that connects this single weekend event to the deeper fragility of the systems we have built. The electrical grid is engineered to withstand a certain spectrum of disturbances. That spectrum was defined using historical weather data. The historical weather data said that a storm like this does not happen in May, so the grid was not hardened for this event. The trees were not trimmed with this event in mind. The emergency response plans did not account for this event. The entire infrastructure of the region is optimized for a climate that is no longer the climate of the present. The gap between what we built for and what is actually happening is the gap where failures happen. Not dramatic failures, not the kind that make headlines for a day, but the grinding, prolonged failures that leave people without power for a week, without water if the pumps stop, without heat if the temperatures stay below freezing for longer than the forecast says. And the forecast for next week is what concerns the people who are watching the longer range models. The storm passes, the snow melts, the wind dies. But the cold air that the storm pulled down from Canada does not immediately retreat. The blocking high over the North Atlantic is still there. The trough that produced the storm is still there, though it will weaken and lift northeastward. What replaces it is not the warm, stable pattern that May is supposed to deliver. What replaces it is a persistent northwest flow, cold air draining down from Hudson Bay, a series of short waves rotating around the base of the trough and delivering repeated shots of unseasonable chill. The high temperatures in the Northeast for the first week of June are currently projected to be 10 to 15 degrees below normal. Nighttime lows will flirt with freezing across the interior. The growing season has started. The gardens are planted. The nurseries have put their stock outside. The assumptions that govern agricultural planning in the Northeast are about to be violated in the same way the assumptions that govern utility planning have already been violated. This is the pattern I want you to hold in your mind. Not the storm. The pattern. The storm is an event. The pattern is a regime. The question that matters is whether the pattern persists, whether the blocking high over the North Atlantic has locked in, whether the jet stream has entered a configuration that will define the early summer of 2025. The ensemble models are conflicted on this question. The European ensemble shows the block breaking down in about 10 days. The GFS ensemble shows the block persisting for at least 3 weeks. The difference between those two outcomes is the difference between an unusual late May storm and a fundamentally disrupted early summer. If the European model is correct, the pattern returns to something like normal by mid-June. The cold anomalies fade. The warmth returns. The growing season recovers. If the GFS is correct, the cold persists into the third week of June. The frost risk extends into the month when the sun is at its highest. The agricultural impacts cascade. The energy demand for heating remains high when it should be near zero. The systems that we built assuming a predictable seasonal cycle are tested in ways they were not designed to be tested. Neither model is certain. Neither model can be certain. The chaotic nature of the atmosphere guarantees that the forecast for day 10 is a probability distribution, not a deterministic prediction. The best we can say is that the probability of a persistently blocked pattern is higher than it should be for this time of year, higher than the climatological baseline, high enough to warrant attention. The question that I want to leave with you, the question that I have been circling throughout this narrative, is not what the weather will be next week or the week after. The question is what it means that our models are diverging so dramatically on the evolution of the large-scale flow. When the European and American models disagree on the fate of a blocking high, they are not disagreeing about a detail. They are disagreeing about the fundamental structure of the atmospheric circulation. One of them is wrong. Both of them may be wrong. The only thing we know for certain is that the atmosphere is doing something that the models did not anticipate, and the models are struggling to catch up. The snow in May is the signal. The signal is real. The signal is telling us that the boundary between the seasons has become permeable in ways that the statistical distributions do not capture. The question is whether we are witnessing a fluctuation or a shift. The answer to that question will not come from this storm. It will come from the accumulation of storms, from the pattern that emerges over the next several months, from the behavior of the atmosphere when we look back at 2025 from the perspective of 2030. But that is an answer for later. What we have now is a storm. What we have now is a configuration that should not be happening in May. What we have now is the opportunity to watch, to measure, to learn, and to ask the question that the models cannot answer. What comes next? Hold that question. Let it sit in the space between the forecast and the reality. Because the storm is not the story. The storm is the entrance to the story. The story is about the assumptions we make about the world and how those assumptions fail when the world changes. The story is about the gap between what we expect and what arrives. The story is about the snow in May and what the snow in May reveals about the architecture of the atmosphere and the limits of our ability to know what the sky will do next. The storm will pass. The snow will melt. The winds will calm. But the question that the storm raises, the question of whether the envelope of seasonal variability has permanently expanded, that question will not pass. That question will sit with us through the summer, through the fall, through the next round of storms, through the next moment when the calendar says one thing and the sky does another. That is the deeper unknown. That is the place where the science ends and the waiting begins. And so we watch. We watch the pressure falls and the temperature drops. We watch the models struggle to keep pace with a reality that is moving faster than their equations. We watch the trees bend and the snow accumulate on leaves that were not built for the weight. We watch because watching is the only thing we can do. The atmosphere does not ask for our permission. It does not care about our plans. It runs its physics, and we live inside the consequences. The snow in May is not a warning. It is not a message. It is just an event, a configuration of temperature and pressure and wind that happens to be happening now. But the fact that it is happening now, the fact that it is happening in May, the fact that it is happening with a magnitude that the climatology says should be impossible, that collection of facts adds up to something that looks very much like a shift. Whether it is a shift or a fluctuation, whether the envelope has expanded or simply tilted, whether the future holds more events like this or fewer, those are questions that only time will answer. Time and the accumulation of data. Time and the slow, grinding work of science. Time and the storms that have not yet arrived, but are already taking shape somewhere over the horizon, somewhere in the cold air building over Hudson Bay, somewhere in the warm waters of the Gulf Stream, somewhere in the blocking high that refuses to move. The storm is coming. The snow will fall. The winds will blow. And when it is over, when the power comes back on and the trees are cleared from the roads and the temperatures climb back toward something that feels like May, we will be left with the question. The question of whether the world has changed or whether we only just noticed how much it always could. That is the deeper unknown. That is the place where the certainties end and the possibilities begin. Hold that question. Hold it with you through the weekend, through the wind and the snow and the dark. Because the answer, if there is an answer, is not here yet. The answer is still taking shape in the atmosphere, in the models, in the long arc of the jet stream winding around the hemisphere. The answer is coming, but it is not here yet. For now, there is only the storm, only the snow in May, only the wind and the cold and the question that will not let go.